Okay. So a sequence of equal periodic payments is called an annuity. An ordinary annuity is one in which payments are made at the end of each time period. The future value of an annuity is a sum of all payments plus all interest earned. And the present value of annuity is its current worth. In these exercises, use future value formulas when present value is 0 and present value formulas when future value is 0. Okay, so down below is just showing you how the future value formula was created. If you're going to make payments over time, so a second payment, a third payment, all the way to your final payment, then that can all be summarized into one formula, which is given by future value equals the payment times 1 plus I to the n minus 1 all over I. Okay. If the account begins at 0 and equal payments are made at the end of each period, the amount in the account, the future value, and payment value are related by the following formulas. So what we're doing here is taking the future value formula above and just solving it for payment, and then we're solving it for n. So here's just the regular future value formula, same one as above, but let's say the problem calls for us solving for the payment. Well, down below, if you wanted to solve for the payment, this is how you would rearrange the formula. Whoops, you would get payment equals the future value times I over 1 plus I to the n minus 1. And if you wanted to solve for n, which is the number of compoundings, then this would be the formula. N equals the natural log of the future value times I plus payment minus the natural log of payment over the natural log of 1 plus I. Okay, so remember that for these formulas, that this is important to know, for all of these, I is always rate, oops, over compoundings. So I is always R over M. Oops, one moment. Yeah, I is always the rate over the number of compoundings, and N is always the number of compoundings times time. So that's sums it up. Okay. So of course, we will practice using these formulas in the problems below. And number 1 says, use the future value formula to find each indicated value. Okay. So they're giving us all the components. All we have to do is plug it in. So here, N is 25, I is 0.4, payments 100, find the future value. So let's go ahead and plug it into that formula above. And you're going to get future value is equal to your payment, which is 100 times 1 plus I, so parentheses, 1 plus I, which is 0.04, raised to the nth power, and n here is 25, minus 1. So that's all in the numerator. And then down below, it's all over I, so over 0.04. Okay, and now we plugged in all the components given the formula above, and now let's type this in a calculator. So of course, I'll use Desmos. Just give me a new one. There we go. Okay, and for Desmos, I'm going to type it in just like I see it. So 100 times parentheses 1 plus 0.04 raised to the 25th minus 1 over 0.04. And here we get $4,164.59. There we go. Okay. And if you're using, if you're using any other calculator that doesn't allow you to put it in like this, to type the input like that, your classic calculator input, what's it gonna be? I'll say calculator. If you're not using Desmos or you don't have a fancy calculator, you're gonna have to type it in like this, 100, and then you're gonna have to do, what's it gonna be? You're gonna have to start a parentheses, and then you're gonna type another parentheses, 1.04 to the 25th minus 1, close that parentheses, and then divide it by 0.04. And that should get you the same result. But use Desmos, it's a lot easier. Okay. All right. Now, number 2. Future value is 2,500, N is 10, I is 0.08. Find the payment. So now we're going to use the payment formula above. Okay. So for this one, payment equals the future value, 2,500 times, and then it's going to be I, 0.08, 0.08 over 1 plus I, 0.08 to the 10th minus 1. And again, let's type it in Desmos. So we get 25 times 0.08 over parentheses 1.08 raised to the 10th minus 1. And here we get 172.57. Okay. So there we've solved for future value. Now we've solved for payment. And of course, the third example, we are going to solve for N using that third formula above. So example 3 says future value is 8,000, I is 0.04, and payment is 500. What is the value of N? So using that formula above, we're going to get N equals, and here you're going to have the natural log of the future value, which is 8,000, times I, which is 0.04 plus your payment, plus 500. And then minus the natural log of your payment, which is 500. All over the natural log of 1 plus your I value, 0.04. Okay, there it is. All the pieces are plugged in where they need to be. And now all we have to do is calculate. And of course, using Desmos, you type it in just like we see it. So I'll start the fraction, and then I will go to my functions, natural log, 8,000 times 0.04 plus 500, close that, minus the natural log of 500 over the natural log of 1.04. And here we get 12.61. Okay. And that's how you use these formulas. Given the certain pieces, plug them in and calculate. Any questions on this page? All right. Keep moving. Okay, next. Number 4, and I'll keep Desmos up because we're going to be using the calculator a lot today. Number 4, USG Annuity and Life offered an annuity that pays 7.25% compounded monthly. If $1,000 is deposited into this annuity every month, how much is in the account after 15 years, and how much of this is interest? Okay. So let's go ahead and label everything we have. So first off, they're giving us the interest rate and the compoundings. So here, we'll start with that. They say I, remember that I is your rate over compoundings. So our rate is 7.25%. So you're going to convert that to decimal, 0.0725 over your compounding. So if we're compounding monthly, that means there's 12 months in a year. So it's going to be over 12. Okay. And now we want to see if this is going to be a nice decimal number. If it's not, we're going to leave it as this fraction. So I'm just going to type in the calculator, 0.0725 divided by 12, and we do not have a nice decimal number. So I'm going to leave it as that fraction. Okay. And then it says that we are putting payments or deposits of $1,000 every month. So they're giving us the payment. Payment is $1,000. And then they're giving us time. How much is in the account after 15 years? Okay. So that means we have enough information to set up N. Remember that N is M times T. It's the number of compoundings times time. So we are compounding monthly, so it's going to be 12 times 15 years. And 12 times 15, what's that? 180. Okay. And of course, we are looking for future value, because we want to know how much will be in the account after a certain amount of time. So we're putting $1,000 payments every month, and we want to know how much money will we have in 15 years. And hopefully we'll have a lot of money. Okay, so let's go ahead and plug these components into the future value formula. Where can I fit that? I'll fit that over there. We have the room. Okay, so future value equals your payments, which is 1,000, times 1 plus I, and our I is 0.0725 over 12, raised to the 1/80th minus 1. So all that's in the numerator. and then we put it all over I, which is 0.0725 over 12. Okay, and of course, using Desmos, I'm going to type it in just like I wrote it. So 1,000 times parentheses 1 plus 0.0725 over 12 raised to the 180 minus 1. And then over 0.0725 over 12. And like I said, I typed it in just like I wrote it. Okay. And then this says that after 15 years of putting in $1,000 every month at 7.25% interest, we are going to end up with $323,000, 943 and 7 cents. That is a good chunk of change to have after 15 years. So this is way better than the last lecture that you guys had to watch, of course, because the last lecture, you're putting in a certain amount of money and you let it sit. This lecture, you're constantly putting money in. You're putting $1,000 in. You're putting $1,000 in every month at a certain interest rate. So the more money you put in, the more interest is what you're going to get back. So of course, this says how much of this is interest? Well, we put $1,000. We deposited $1,000 every month for 15 years. So that means that we put in here. Let me do this. So we put in $1,000 every month for 15 years. So that means we put $1,000 in for 180 months. So this means that if there was no interest, if we were just putting this into a bank account, we would have only made $180,000. Well, since we put it into an account that gains interest, to find the interest, we just take 323,000 and subtract it from 180, and that will give us our interest earned. So 943.07 minus 180,000 says that we gained or earned $143,000, 943 and 7 cents in interest. That is some interest I would like to have. So that's $143,000, almost $144,000 in free money over 15 years. So that is the way you guys want to invest. So that's interest. Okay. So that is, again, another future value problem. Any questions on that? All right. Let's keep going. 5. A self-employed person has a retirement plan. If deposits of $7,500 are made each year into an account paying 8% compounded annually, how much will be in the account after 20 years? So again, we want to know how much will we have at the end in 20 years. Okay, so let's go ahead and write down what information they're giving us. So here they said that we are making payments of $7,500 every year. Okay. So payment is 7,500. And then I is going to be rate over compoundings. Well, we are getting a rate of 8%, so 0.08. And we are compounding annually, so that is good. That means that it's over 1. How many years are in a year? 1. So I is just 0.08. Then for N, which is compoundings times time, well, we are compounding every year, and we're doing this for 20 years. So N is 20. All right, we have all the pieces we need, so just plug them into the future value formula. Future value equals 7,500 times 1 plus I, which is 0.08, raised to the 20th minus 1, over 0.08. And now type it in the calculator just like we see it. And I don't think I need an actual graph. So let me just go back to Desmos and just use the calculator that they have, just the scientific one. There we go.
Professor,
what's up?
I'm a little confused on N.
Uh-huh.
Where are you getting the 1.2?
Oh, it's 1 times 20. Sorry.
Oh, okay. That's my bad. All right.
There you go. $7,500 times parentheses 1.08 raised to the 20th minus 1 over 0.08. And after putting in $7,500 a year for 20 years at 8% compounded annually, we end up with $343,000, 214.73 cents. Not bad. So that's how much money this self-employed person will have at the end of 20 years if they put in $7,500 a year. That's some good money right there. Okay. Any questions on that?
No, sir.
All right. Next, let's do it again. Okay. 6. Let me get rid of that. There we go. The Hartford offered an annuity that pays 5.5% compounded monthly. What equal monthly deposit should be made into this annuity in order to have $100,000 in 10 years? Okay. So now we are looking for how much should we pay to get $100,000 in 10 years. So here we are looking for the payment. Okay. So let's go ahead and put together what we know. And from our problem, it says that we're getting 5.5% compounded monthly. So that means we could put I together. So this means that I, again, is the rate over compoundings. We're given 5.5%. So that's 0.055 over, and we are compounding monthly. So that's 12 months in a year. Now, again, let's see if that's a nice decimal number. I doubt it, though. 0.055 divide 12, and it is not. So we will leave it as that ugly fraction. Okay. All right, and then it says what equal monthly deposit should be made into this annuity in order to have $100,000 in 10 years. So they're giving us the future value that we want. We want to have $100,000 And then we can find N, which is M times T. We are compounding monthly, so 12 times, and we want to do this in 10 years. So that's 120. Okay, and all we're looking for here is payment. So we will use the payment formula that's on the first page. So let's go ahead and plug in, again, everything that we know. So here we'll get payment equals 100,000 times, I think it's I, which is 0.055 over 12 over 1 plus 0.055 over 12 raised to the 1/20th minus 1. There it is. And again, that's exactly what we are going to type into our calculator. So here we go. 100,000 times parentheses 0.055 divide 12 over 1 plus 0.055, oops, forgot a 5, over 12 raised to the 1/20th minus 1. And in order to have $100,000 in 10 years, we need to deposit $626.93 every month. All right. That doesn't seem too bad if you don't have student loans. Okay. Any questions on that one?
No, sir.
All right. Okay. Next. So a sinking fund is an account established for accumulating funds to meet future obligations or debts. Sinking funds are money you set aside each month to pay for quarterly, semi-annual, or annual bills. It is sort of your own escrow account that you set up for yourself. So when an irregular bill comes up, you aren't scrambling for money. They are designed to keep you financially afloat when something occurs that needs a bit more money than you brought home from your paycheck. Basically, they keep you from sinking financially. So a sinking fund or a nest egg or an emergency fund, I don't even know if people have those anymore. But it would be great to have one, some backup money. Always ideal. Okay. So example 7. A company establishes a sinking fund for upgrading office equipment with monthly payments of $2,000 into an account paying 6.6 compounded monthly. How long will it be before the account has $100,000? So this time we're looking for time, because it says how long will it be? So they gave us the payment, they gave us the future value, they're giving us all the information. So our job now is to solve for N. Okay, so let's go ahead and put all the components down that they're giving us. And they said that our payments are $2,000. Okay. And then it says that it's going to an account paying 6.6 compounded monthly. So I is rate over compoundings, and it's 6.6, so 0.066 over 12. Let's see if that's a nice number. You never know. 0.066 divide 12. And it is, you get 0.0055. Now we'll use that decimal number only because it's a nice decimal number. Okay. And then it says, how long will it be before the account has $100,000? So they're giving us the future value, and they're giving us $100,000. So what we have to solve for here is N. But remember that N is also M times T. So that's going to come back when we get to the end. Okay, so now let's plug this in for the formula for N, which deals with all those natural logs. So you're going to get N equals the natural log of your future payment, 100,000, times I, 0.0055, plus your payment of 2,000. So plus 2,000. And then minus the natural log of your payment. Minus the natural log of 2,000. Okay. And then you're going to put it all over the natural log of 1 plus your rate, your I. So 1 plus 0.0055. Okay. There it is. And let's go ahead and type it in. All right. So Desmos, here we go. I'll start the fraction button first. And where's my natural log? Click functions. There we go. Natural log of 100,000 times 0.0055 plus 2,000. Close that, and then minus the natural log of 2,000 over the natural log of 1.0055. And we get 44.29. Okay, but we're not done, because remember, I said that N is also the formula M times T, compounding times time. Well, guess what? We know how many times we're compounding. So this formula is actually not MT, it's going to be 12T. So what we're going to do next is let 12T equal 44.29. So we get 12T equal to 44.29, and 44.29 divide 12 will give me 3.69. Okay, so now remember, for these problems, time is always in years. So if time is 3.69, we can say 3.69 years, but if my math lab is picky, it's either just going to say 4 years or 3 years. So however I want you to round. But since it's 3.7, let's just go ahead and say 4 years. Okay. And if it doesn't take 4, maybe try the 3.7. If it doesn't take 3.7, maybe try 3. You know how picky it is. But I'm assuming since we are 3.7, we should just round up to 4 years. Okay. Any questions on that one? All right. Okay. Last one. Number 8. You wish to save money for your child's college education. You start depositing $900 each year into an account that earns 8.1% compounded annually on your child's 3rd birthday. On your child's 17th birthday, you make your last deposit of $900, which is 15 equal deposits in all, with no additional deposits. With no additional deposits, the money in the account continues to earn 8.1% interest compounded annually until your child is 21. How much is in the account on your child's 21st birthday? All right. Okay. So what we need to start first is we need to find the future value of the money you've been depositing so far. So that's what we need to find first. So I guess we can make that a step. Let me see. We'll call it A. Find future value. Okay. And now let's go ahead and list the components. We are making payments of $900 each year. So we're making a payment of $900. And this payment is going into an account that earns 8.1% compounded annually. So this means we can find I. I is R over M, and we're getting 8.1%. So that's 0.081 over, and we are compounding annually. So that means you get 1. So this gives us just 0.081. Okay. And then we started on our child's 3rd birthday and finished depositing on the 17th birthday, which is 15 deposits in all. Okay, so this means that we deposited money for 15 years straight. So this means to find N, remember N is M times time. We are compounding annually, which is 1. And the years, so since from the 3rd birthday to the 17th birthday, we started depositing on the 3rd birthday. That's why it's 15 equal deposits in all. So 15 years, and N is 15. All we have left to do is find the future value now. So future value equals our payment times 1 plus I, which is 0.081, raised to the 15th minus 1, all over I, which is 0.081. And on your kid's 17th birthday, let's see how much money they're going to have. 1.081 raised to the 15th minus 1 over 0.081. And on your child's 17th birthday, they will have $24,627.93. So there's the future value. So this means we're not making any more deposits after the 17th birthday. So now we're going to take this future value and let it sit in the same account that earns 8.1% interest until the child is 21. So now this means that we are going to use compound interest. So now we want to find the final amount on the child's 21st birthday. So we'll call this B. We're going to say use compound interest. And remember that from last time, it's A equals P times 1 plus I to the N. And the beginning amount is going to be the amount we left off with on the 17th birthday. So P is $24,627.93. And then I should be the same as above. Rate over compoundings. It says that this account still earns 8.1% compounded annually. So yeah, it's the same as the above, so 0.081. And then N, this is going to change. We are still compounding annually, so that's M times T, so that's 1. But now we're going from the 17th birthday to the 21st birthday. So this means we are waiting 4 years to see how much money is in the account. We are no longer making deposits. What we're doing is letting that $24,000 sit in there for 4 more years. Okay. We have all the components. So let's go ahead and find A. A equals 24,627.93 times 1 plus 0.081, all raised to the 4th. So the final amount of money on your child's 21st birthday, 1.081, right? Yep. Raised to the 4th will be $33,630.30. What is a 21-year-old going to do with all that money? Okay. And guys, that is future value. And we are done.
Professor, I actually had a question about the actually, did you fix it already? The work shown for 3.3 is due this Thursday, but the actual assignment isn't.
Okay, so I'll go ahead and look at due dates then.